Hello everyone. In this video, we are going to cover the second part of relativity chapter, that is space-time diagram. And we are going to learn everything related to space-time diagram along with how to apply them in the certain problems. Okay. So in front of you is a space-time diagram. We will try to break it down as simple as possible. So first we will just look at the axis, the space axis. Okay, so all the x, y, z axis is combined into a one space axis. Usually, since we are doing one-dimensional relativity only, so our x-axis represents our space coordinate or space axis. It can be given in meters or light years or any other unit, and this also represents our rest frame, that is S frame. Okay, now corresponding to this frame, there is a time axis as well. Now, time axis is given as c times t, so such that it has the same units as a distance, because speed into time is distance, but it represents time axis. So this is our time axis. Okay, so once we know what is space and time axis, we usually in the questions you will find that the space and time axis are drawn on the graphs, and like a defined scale is given to each of the coordinates. Okay, uh, now imagine in this the 0, 0 position represents present, like at time t equal to 0, the position is 0. Now, if there is a rocket or some kind of a spaceship that is moving in space and time simultaneously, so it will trace a line that is inclined with the time axis. And this is something that is called as a world line. A world line is a set of coordinate or the line traced by an object moving in space time. Okay, so there is an object in a spaceship that will be moving along this line. Okay, and let's say we are trying to figure out the time measured by the person in the spaceship. So we will have named this as CT dash axis. So this is observer 2, this is observer 1. So corresponding to this time axis, there will be a space axis as well. So there is nothing moving along the space axis of the S dash frame. It is just that what will be the space coordinates measured by the S dash frame can be traced on this axis. And they both make some angle theta with the horizontal and the vertical. Now this angle theta is same. Okay, and we can see that there is a relationship for this theta. This theta can be given as theta is equal to tan inverse of v by c. So the v is the speed of the rocket. So v is the spaceship or speed of the moving frame, I can say. S dash. Okay, and it can be written, it can be taken as this distance. So if I take this distance as my x and this distance as my, let's say, ct, then it can be x by ct. So don't get confused about it. It is a position or time. It is just that if I measure on the graph this much length and this much length, like it can be opposite side upon adjacent side of the triangle that the axis trace. And this is how we can determine the theta as well. Okay, so determining v by the graph is also simple. You just have to take the opposite side and adjacent side. For any line on this graph, you can take this as well. It doesn't matter. And we can get the v by c. We will look at that in the problem as well. Okay. Then once we get the space axis for both the frame, we need to understand that if v is equal to c, then tan inverse of 1, it will be c over c. So tan inverse of 1 would be equal to 45 degrees. So theta becomes 45 degrees. So the light, usually a photon, is traveling in this direction, and it has a world line which makes an angle of 45 degrees with respect to the time axis. Okay, so this is a world line of a photon. Okay, now it is not necessary the photon will move to the right only. If the photon is moving to the left, we can draw same 45-degree line in this direction as well. So it indicating the light is emitted in all the direction. Okay, now on the left axis, you will see there is a left, means any object that is moving to the left will have along the left, and on the time axis, the negative time axis, this indicate past. So below is past and the future is as we go up vertically. Now we can talk about a point or an event in the space-time diagram. If there is some doubt at this point in space-time diagram, it's completely fine. When we will do the problems, we will understand uh, what are the required things, okay, and we will focus only on that. Okay, so there are certain rules to understanding space-time diagram. Once you understand the rule and accept them as they are, then it is easier to work with them. Okay, because the Euclidean geometry and how this is representing this is something that is required a little bit complex maths, which we don't want to get involved and which is neither required as well. So we will just stick to basic and learn some rules of this. So the rule number one is that if there is an event, usually this event represents a space and a time coordinate. So in S frame, the space coordinate, if I want to find space coordinate, what we usually do is we take a line and draw parallel line to the space axis. Sorry, time axis. To get the space coordinate, we draw a line parallel to the time axis. Similarly, if I want to get a space time coordinate, I will draw a line parallel to space axis in the S frame. Similarly, if you want to calculate a position coordinate or the space coordinate in S dash frame, we will draw a line parallel to the time axis of the S dash frame, that is CT dash. And similarly, if I want to get time for this event according to CT dash frame, I need to draw line parallel to space axis. So if I want time, I will draw line parallel to space axis. If I want space coordinate, I will draw line parallel to time axis. In both the frame, it works. Okay, giving us both these coordinates. Okay, so these are the basic things that we like to explore, and how this is applicable is something that is important. If I have a vertical line, what does a vertical line represent? It represents a space time or the world line of an object that is stationary. So stationary object has same position, but the time is not pausing for that object. So the world line will be vertical. Okay, and no object can have a world line that goes beyond 45 degrees with respect to time axis. So that is also very much important. There is two rules that we will like to explore. This is rule number one. If I have a event and I want to calculate the, let's say this point is where I want to calculate, okay, something. So what we will do is, like, usually what the CT dash axis and X axis are not clearly scaled so that we can get a particular measurement of this from the axis. So usually what we do is, like, if I want some measurement on this axis, I will draw a corresponding horizontal line and see what is the measurement on this axis. Let this be some CT. If this is some CT, then all I need to do is divide by gamma factor to get CTA. Okay, this is CTA. So even if the axes are not grid, like the scales are not given on this axis, we can still find a particular coordinate by taking corresponding coordinate on the CT axis and divide it by the gamma factor. So if it means if I have if I want to see where is the one on this axis, okay, on this horizontal axis, so I will just take, let's say this is some CT dash, okay, some CT. Then the relationship will be 1 will be equal to gamma over CT, and it will be gamma is equal to CT. So it means this much will be the gamma. It means since gamma is always greater than 1, we will have a dilated time on the CT axis, and this will be much more like a proper time. Okay, so these are the basic things that we will like to remember. Okay, so this will be dilated time. Okay, similarly, if I want to, like, in a frame of S dash, that is in this moving spaceship, if the object is stationary, okay, okay, then if I measure some length L0 in this frame, and if I measure a proper length of this frame, that is L, okay, sorry, so L0 is the proper length, okay, because it corresponds to the same time. So we can get a contracted length, that is L, by taking L naught over gamma factor. Yeah, this L will be contracted, okay, because it is stationary for the x dash axis because it corresponds to a single time coordinate. Okay, so that's how we can correspond this. Okay, so we can find the corresponding measurements on this axis as well. Okay, so if I have something like this, I can divide it by the gamma factor. So gamma factor is usually the conversion factor between the coordinates of space axis and the time axis as well. Okay, so how this will be applied, let's see. In this question, the space-time diagram is in reference frame is given for observer O on the Earth. So this will be my S frame. So each observer O and the spaceship A, which is my S dash frame, okay, are at origin initially. The world line of spaceship A is given. So this is a world line of spaceship A is given. And you can see that on the X and CT axis, everything is given. Every coordinate can be given, measured, but nothing given on the CT dash axis. The question says calculate in terms of C the velocity of spaceship A relative to the observer O. Now, how to calculate velocity of A? We need to measure this theta. Correct. Now this theta, as I mentioned, the tan theta is equal to V by C. Now what will be the tan theta here? So if I take this coordinates, this will be opposite side. So opposite side is opposite or adjacent side. If I do opposite side is like roughly around 1.2, and this adjacent side is 2. So 1.2 over 2. Okay, if I do, so V by C is 1.2 over 2, which is equivalent to 0.625. So that is something that we will get here. Okay, so this is the basic idea of calculating V from the graph. The next part of the question, draw is x dash axis. Now x dash axis will have the same orientation, same angle, but with respect to the space axis. So what I will do, I will draw a straight line. First, I need to mark that point similarly. So 2 up and 1.2 to the right. So similarly, 2 to the right and 1.2 to the up. So something here. So then I will draw a straight line passing through this. Okay, we will try to make it as much precise as we can so that. Okay, so let's say this is our x dash axis. Now, once we get through this, the next part of the question is the event E is the emission of a flashlight. Observer O sees light from the flash when t is equal to 9 years. Calculate it calculates that the event E is 4 light years away from position positive x direction. Plot the point E on the graph of the space-time diagram, label it E. So two information is given. Observer O observes the light from the event E at 9 years, time equal to 9 years. Observer O is a rest frame object and it measures the event E which is 4 light years away with respect to the observer O. So observer O is the rest frame, so this is S frame. So it can be anywhere on this straight line. Okay, on the 4th light year, it can be anywhere on this 4th line because it is measuring 4 light years. Okay, now it detects the light at 9 years. So this is 9 light years, but it is CT. So it is CT will be 9 light years. Okay, now where it will be the event T, what we can do is we can retrace the light. Now, whenever the light is coming, we need to know that the light usually travels at the world line of light is always 45 degrees. Correct? So it has to make an angle of 45 degrees. Okay. So if the light was emitted from the event E, it will travel in a world line of 45 degrees with respect to vertical. So this is with respect to vertical. And this point is at, this point corresponds to event E because it has a space coordinate of 4 light years. Okay. And it has to be emitted somewhere in past because this is like the time when O observes the light. Okay, and this is the time of emission. Okay, so this has to be clear. So the light emitted from this and then eventually reached this. So this is how we calculate the position of event E. Okay. Now the question says, after getting the determine the time according to spaceship A when the light from event E was observed by observer A. So whenever observer A is the world line of observer A is this. This is the world line of observer A in the spaceship. So basically, when this will be coinciding with this axis, whenever there is a coincidence, this is the observation point. So this is the time when observer A observes the light from him. Okay, and we want to find the time. Now, time, what would be the time on this? So what we will do, as we mentioned here earlier, if I want to find a corresponding time on this, I will just find this time. Let's say this is the corresponding axis. So corresponding here, time is roughly around 5.6 light years. That is a CT. So whatever we will do, since we know this time, CT dash time will be 5.6 light years over the gamma factor. So gamma factor we need to calculate first by taking 1 over root of 1 minus 0.625 square and then substitute here to get the answer. Okay, this is what we did, and we got roughly around 4.3 light years. Okay, 4.3 light years. CT dash is 4.3 light years, but 1 light year is speed of light into 1 year, so it is 4.3 years. Okay, so this is how we supposed to do the problems. We'll look at one of the another examples. A train is moving across a bridge with a speed of v is equal to 0.4 c, and observer A is in rest in the frame, and observer B is at rest with respect to bridge. The length of the bridge according to observer B is 2 kilometers. What is the length of the bridge from the observer A's perspective? So for B, the bridge is stationary. So the bridge will be a proper length. So this is a proper length. So for A, it will be contracted length. So for first time, we will calculate the gamma factor and then use the length contraction factor. So length A 2 over gamma factor. So gamma factor will give you 1.09. This is a contracted length. Okay, 1.09 kilometers according to observer A. How much will be the time taken to cross the bridge according to observer A? So observer A knows that its speed is 0.4 c, and it knows that the length of the bridge is 1.09 kilometers according to it. So it will cross in the time of, so we just do distance over time because no need to calculate relative velocity. We know the length in the direction, in the length from the perspective of A and the speed of the A we know. So we can calculate the time directly, and we will get 9 into 10 raised to minus 6. Okay, seconds. Then the why the B is stationary, because bridge is stationary with respect to B length. So LB becomes proper length. So here comes the space-time diagram question. According to observer B, the two lamps at opposite end of the bridge are turned on simultaneously. Okay, so there are two lamps given and they are turned on simultaneously according to observer B. Now, event X is the lamp being turned on. This is very much important. The lamp being turned on is the event X, and event Y is also lamp being turned on the other side of the bridge. X and Y are shown on the space-time diagram, the events. Okay, and obviously the distance is 2 kilometers between them according to observer B, and also the world line of observer A is given. Okay, now draw a line of space-time diagram from the reference frame of A. So x dash axis, we can see that this is if I refer to this point particularly, so this is the opposite side is 2 blocks and or adjacent side is 5 blocks. So I will take the corresponding 5 blocks, 2 blocks, and I will draw a straight line passing through this. Okay, so this is our axis. I will label this as x dash axis. Then demonstrate using the graph which lamp, according to observer A, was turned on first. So observer A, we have CT dash and X dash axis. Which event happened first? So the time coordinate, corresponding time coordinate for this event X and Y. See, events are simultaneous in space. That's why they are on the horizontal line. They are simultaneous, but they are not simultaneous in the uh, CT dash frame or the moving frame. So how do we find the time coordinate corresponding to this? We usually draw a line parallel to the space axis. So if I draw a line parallel to space axis and see where it meets the time axis, and I will draw another line. So we can see that wherever it interacts with this point, this is the time when Y was turned on, and this is the time when X was turned on. So we can clearly see from the graph that event Y happened before event X according to observer A. So from the time coordinate, we should always draw why event Y occurred first. The next part of the question is demonstrate using the graph which lamp observer A observes first. Now you try to understand this. In relativity, things are different than the usual surrounding observation we have. Usually, when we see that a light being turned on, when I press a button, the light is immediately turned on. But in the cases of the relativity and the speeds that the objects are moving, the light pressing a button, like light being turned on, and then receiving that light are the two different events. Okay. So when they say A observes the light first, is basically light will be emitted from X and Y, and then it will be reaching to observer A. So when we see light, when we talk about light being observed, we always refer to a world line of the light. So world line of the light will be always be at like 45 degrees. Okay, with respect to axes. So 45 degrees, I will draw a world line from a photon emitted from lamp Y and where it intersects with. So this is our axis. Okay, I will try to draw as much accurate as I can. Okay, this is fine. Similarly, a photon will be leaving X as well. So I can use the grid as a reference because the diagonal of this square boxes will be something that will be at 45 degrees. So we can see that there are two things that I can observe. So this says that the light from lamp X was observed first compared to the. So you can see that these points represent something. So the space-time diagram is something that answers our questions in this way. Okay, mathematical calculation can be avoided just by using space-time diagram. Okay, now what else they have given? Determine the time according to observer A between X and Y. So between X and Y, the time difference is basically this much, correct? Now this much time difference, there is no grid. The grid is not detailed enough to get the corresponding time difference. But what we can do is we can use our, since we, for this question, we can see that the information that we know is delta T is 0 for the S frame because, or the B frame we can say, because they are simultaneous. And the distance between those X and Y is 2 kilometers. Similarly, for H dash frame, the distance is 1.09 kilometers that we calculated X dash, and delta T dash is something that we are supposed to calculate. So we can use our basic Lorentz transformation. T dash is equal to gamma times delta T minus delta X. This will be over C square. So if we use this, we can get the answer, or we can use space-time interval. In space-time interval, we can use delta x dash whole square minus c delta t dash the square is equal to x delta x square minus c delta t square. So this is a space-time interval. They are equal in both the frames. So we can just substitute and calculate the values of delta t dash. Remember to convert this kilometer to meters and substitute c value as 3 into 10 raised to 8 meter per second to get the t dash. Okay, so this is how we use a space-time diagram. These are the basic examples how the space-time diagram can be used to solve relativity problems. Okay, so that's it. Thank you so much, guys.